everyone. This is the 7th lecture of the Chemical Oceanography module, and it's a continuation of primary productivity. It's not a super long one, just a dive into some factors that control primary production in the ocean. So the first and the major factor that impacts primary productivity is nutrient availability, and this includes the macronutrients like nitrate and phosphate, as well as micronutrients such as iron, and if there are diatoms involved, then silica. A lot of nutrients in the ocean come from river runoff, and this, as a result, means that productivity tends to be higher along continental margins. And if there aren't nutrients, then productivity will be greatly limited. And also just a reminder that this links back to the Redfield ratio, that the carbon to nitrogen to phosphorus needs to be available in a ratio that it can be used by phytoplankton. The other most important factor limiting primary productivity is sunlight or solar radiation. As I said in the previous lecture, greater than 99% of primary productivity is driven by photosynthesis. And the photo is where the light comes from. So as a result, the light is most prevalent in the top layers of the surface seawater. And if you're in a very shallow area, the light, of course, can reach all the way to the seafloor, for example, in like a continental region. And we tend to define the upper sunlit layer of the ocean as the euphotic zone, which typically extends from the surface to about 100 meters. More commonly, the euphotic zone is defined as where the 1% light level. And essentially, the euphotic zone defines where there's enough light for photosynthesis to take place. And here I think this image shows really nicely with depth on the y-axis now, and you can see not looking very deep in the water column, 300 meters, that the rate of photosynthesis, which is in green, reaches a maximum in the surface and then starts to decline as light starts to decline. And that respiration, which is also happening at the same time, which is essentially the reverse of photosynthesis, is the rate in orange here. And this is happening at the same rate regardless of depth because it's not dependent on light. And at some point, which is denoted right here, where the rate of photosynthesis is equal to the rate of respiration, this is known as the compensation depth. So above this compensation depth, you have net primary production, and below this compensation depth, you have net respiration. So upwelling is a big contributor to nutrient supply in the ocean, and you'll learn a lot more about the physics of upwelling later on in the course. But remember from the nutrient lecture that the deep ocean has much higher nutrient concentrations than the surface ocean. So if you can find a way to get that deep water to the surface, it'll make the phytoplankton very happy, right? Because it gives them access to nutrients. So that's what upwelling does, is it takes cooler, deeper seawater that's nutrient-rich and brings it to the surface. And so anywhere that you have upwelling, which happens along the equator and as well as along the coast, are areas of high productivity. Here you can see in this sort of handful of cartoons where upwelling tends to happen. And if you notice, it tends to happen on the western side of continental margins, so the western side of South and North America, Northwest Africa and Southwest Africa. This is the Benguela upwelling zone on the west coast of South Africa here in red, and there's a blow up of that here. And there's an upwelling zone in Australia as well. And there's a reason that it happens on the western edges that I'm not going to get into too much here, but suffice it to say that it's a combination of the direction the wind blows and the direction that water moves as a result of the wind blowing. And it leads to this deep water coming to the surface. And this is indicated by this, what you can see on the left here, this satellite image of South Africa and Namibia, the waters off the west coast. This is showing satellite view of chlorophyll. And chlorophyll is used as a really good proxy for primary productivity because chlorophyll is a pigment that's used in photosynthesis. And so if there's a lot of chlorophyll, it means that there's a high concentration of photosynthetic organisms, and there's then an assumed relationship between that and primary productivity. And so all of these red filaments that you see on the coast here are due to that upwelling of deep waters with a lot of nutrients, and so then there's a lot of biomass. This is a global view of chlorophyll on the ocean. You can see here the purple to red scale. And then it's also compared to land normalized chlorophyll. So you can sort of see the distribution of photosynthetic pigments around the ocean and the land. And again, just a reminder of the distribution of primary productivity, that it varies geographically. So you can see here the difference between the polar ocean, the temperate oceans, and the tropical oceans. And it also varies strongly seasonally, particularly in the temperate and polar oceans, whereas the tropical ocean doesn't have a lot of seasonal variability. And that this difference in productivity between seasonal and spatial differences are driven by these combinations of light and nutrients. And here, this is, I think, a nice little schematic that highlights that we have the net production. So new production comes from nutrients supplied by upwelling, and that's your blue line here. And that's referred to as net ecosystem production, where nutrients come in, they're consumed, and then they get exported out of the surface ocean. And then we have our regenerated production, which is in red. And so this is the nutrient recycling here that happens. And so then nothing is coming into or leaving the surface. So we've got that. And then also that the phytoplankton themselves do a little bit of respiration. And that's this green arrow here. And when we think about gross primary productivity, it's all of these things together, the blue plus the red plus the green. And then when we define net primary productivity, it's the blue plus the red, and then it's subtract out the green. So you take out the respiration there. And so net primary productivity is all of this organic matter that's available for the rest of the ecosystem. And then here again, this is an image that I've showed before, but it kind of brings some of these ideas together. Focusing again on the surface ocean here, we're at 300 meters. So you've got, and this is focused on the tropics or subtropics, where you have really warm waters at the surface, and so you have this stratified mixed layer. And then at depth, you have this strong thermocline, so it's keeping these deeper, colder waters separated from the surface. You've got light in the yellow here that fairly rapidly gets attenuated, and so you get to this 1% light level fairly quickly, so at about 100 meters. Just about below, let's say, 120 meters here, you no longer have enough light for photosynthesis, so now you're light limited. And of course, in the deeper waters are where you have the higher concentrations of nutrients given by the purple here. And so where you have some nutrients and some light in this region is where you have your chlorophyll maximum. And that's your DCM here, your deep chlorophyll maximum. And you can see, so where you have light and nutrients, you're going to generate particulate organic carbon. So this is your organic matter, your biomass that you're generating through photosynthesis. So you can see it's at a maximum there in that mixed layer. And then everything is declining below the euphotic zone, below the mixed layer. So you've got below about this line here, you've got your colder waters. Sorry, you can hear my son yelling in the background probably. You've got your organic carbon here that's being respired, so concentrations are going down, and you're getting these inorganic nutrients then to come out into the water column. And so this is where your respiration is happening. And so lastly, this is on the top panel is a satellite view of chlorophyll A concentration. And it's the summer in the northern hemisphere on the left, and then summer in the southern hemisphere on the right. And so you can see, for example, in the poles, you've got your maxima in chlorophyll in the northern hemisphere summer in the high latitudes, and then likewise in the southern hemisphere summer, your high latitude chlorophyll's at a maximum here. And what you can see is that areas of higher productivity are these areas where there's upwelling along the west coast margins. And you can also see the same along the equator. There's some areas of upwelling that lead to chlorophyll buildups there. And the bottom panels here show surface nitrate. And you can see where that surface nitrate is being upwelled in some areas, and it's directly leading to that productivity. So that upwelling leads to that productivity, that upwelling leads to that productivity. And you can see in, for example, if you look at the Southern Ocean, in the Southern Ocean winter, there's plenty of nutrients because these are really high nitrate concentrations, but there's not enough sunshine. And so finally in summer, when you get some sunlight, you can see the nutrient concentration start to decline a little bit, and you can see this biomass starts to bloom here.